All right, for our last presenter for this breakout session is a name I hope I do not butcher. It should be easier. Nick Martin. Nick Martin's with the Southwest Research Institute, and the floor is all yours, sir.
Thank you. All right. My name is Nick Martin. I'm a scientist with Southwest Research Institute, and I'm going to talk about quantifying potential changes in recharge from changes in weather patterns. This work, well, first, if you don't know about Southwest Research Institute, we're an independent, not-for-profit research organization. And so one of the things we do within the Institute is we have internal research and development grants and programs. And so this work is part of one of those internal research grants. At the time, I applied to give a talk at this conference. I was assuming I would be much further ahead in my internal research than I currently am. So this talk is going to be much more about methods and data than it will be about results. But that probably fits in with the subject matter for this track. So, all right, so start out talking about just recharge in general, mostly just to introduce the topic. But so, sort of the classic definition for recharge from more of a groundwater modeler standpoint would be precipitation falls on the ground surface. And usually this is where maybe the rocks that form the aquifer are exposed at the surface. So the precipitation falls on the surface and then percolates downward to saturated groundwater. That amount or rate of water is recharge. And so it is oftentimes expanded to include more inflows to an aquifer, like things from stream, groundwater interaction, and things like that. And so, what recharge is, we say it's, form of some portion of precipitation that goes to saturated groundwater. And then why is it important? It provides the water to the aquifer that then is available to, increase the amount of water available in the aquifer or to replenish from pumping, things like that. Okay. So with recharge, it kind of provides the interface between the watershed water balance and the groundwater water balance. And so, it is the water coming down from the watershed in this instance that then meets the saturated groundwater. And so if you're thinking about, quantifying recharge, you're going to calculate recharge, and what you're going to look at usually is you're going to look at more of a water balance calculation. And so that would be taking precipitation that falls on the watershed and partitioning it out into evapotranspiration and stream flow. And so, you're starting with the precipitation input, the weather input, and you're eventually trying to, decipher out or take out what becomes recharge. Okay? And so in thinking about that calculation, they're sometimes helpful, again, because we're looking at quantifying out recharge. It's somewhat helpful to look at sort of a dimensional analysis on the time scales. So we're going from precipitation, in this case, to estimate recharge, right? And so with precipitation, there's a wide variety of scales that can be important depending on what you're interested in. In the same way for, your surface water movement, your runoff. And then once you're in groundwater, if it's more of a porous media groundwater, it's a very slow scale compared to, if it would be a karst system, which would be much more like surface water. But the real thing is here with precipitation, you're looking at, usually if you're looking at the runoff portion, you're looking at like an hour. That's kind of the scale of interest to find out. So that's will play into how we'll, decipher out recharge from the weather patterns. So just to sort of reiterate that this is, when we're calculating recharge and we're using sort of a water balance approach, it is, we are calculating sort of the full watershed water balance. So, we're saying recharge here, but we are also getting, stream flow generation, the rest of the watershed water balance. And of course, the stream flow generation portion could be very important for any areas where you have stream flow interacting with an aquifer. So that would be sort of a secondary or supplemental part of the recharge, supplemental recharge component, say. Okay? So just to kind of wrap up the recharge portion of this, what the important points for this is, we're going to look at weather patterns to decipher recharge, right? And so using the weather patterns, we need to look at a fairly fine or high resolution time scale, because we're going to go from precipitation and then discern out recharge. If we had a recharge amount and we were just applying that to, say, a groundwater model, we could do a much longer time scale, say monthly or annually. But because of the thing to discern the impact of recharge from changing weather, we're looking at a watershed scale, and so it's a much finer time scale. Okay. All right. And so looking at quantifying changes in recharge from weather patterns. And so it's just probably a good idea to give just a little overview, definitions between weather and climate. So weather is kind of short term, what's the air temperature right now, what was the amount of precipitation today, things like that. Climate is an average of weather over at least a 30-year period. So long-term average weather pattern. So that's what climate is. Needs to be at least a 30-year period, could be a longer period. And of course, depending on what your time scale of averaging that weather is, you'll get a different average answer. Okay? So climate is composed of both, the time scale duration you're averaging over is very important in terms of the description you get back for climate. All right. So with the weather and climate, when you factor that in with how we're going to calculate recharge, so we'll use weather to calculate recharge because we're doing the watershed water balance. So we're talking about daily values for weather parameters. But then to look at how those average weather patterns impact recharge over a long time period, we need to use at least a climate scale time period, which would be 30 years. So really what you're doing to sort of quantify the change in recharge, you're looking at daily weather and how that produces recharge and what that integrates to over, say, a minimum of 30 years. So the real sort of focus of this work and this study is we want to compare what happens, weather versus any future changes in weather, okay? And we need to keep those separate. So we're kind of setting up a numerical experiment almost. And so with that, we're going to apply sort of a black box watershed model to determine what the recharge would be. And so we're calling it a black box watershed model purely because all we really want from this is to say, if I give it the same, precipitation value and the same air temperature value, I get the same recharge out eventually, okay? So the idea is we have two separate tracks. Historical weather data provides one set of precipitation and temperature values, and then climate change or changing weather patterns would provide another set. And if those are different, we should get, a change in relative recharge. We're not saying how that's going to change things. It is a daily calculation. The watershed water balance is a fairly complicated system. And so depending on what happens with changes in evapotranspiration versus runoff, just increasing precipitation does not necessarily mean you'll increase recharge, okay? So that's, that complexity is factored in. All right. So when you're applying sort of this black box water balance model, there's a number of these out there. They're all publicly available. Well, not all of them, but many are publicly available. The one that's shown, a schematic is shown for right here. This would be, I believe, yes, the USGS's PRMS model. But the point with this schematic is showing, okay, your inputs are your weather parameters, precipitation, air temperature. The model takes care of calculating what would be the final recharge, based on your system, okay? And it also will calculate stream flow generation as well as evaporation and evapotranspiration. So the real focus then is quantifying how recharge changes given any changes in long-term weather patterns, okay? So what we need to do that to sort of implement our numerical experiment, if you will, is we need a model, our black box watershed model, right? And all we want there again is that, if you provide the same air temperature and precipitation values, you get the same values out for recharge and stream flow generation. Okay. The next thing we need is a way to produce a daily time series of precipitation and air temperature that represent historical data. And then we need a complementary time series, again, precipitation and air temperature, that represent, hypothesized changes due to changing in average weather patterns. Okay. And the final sort of component that's needed is a way to link between the historical data and the climate data to say we're comparing, on the same basis. We know we're comparing apples to oranges because they're supposed to be different, but we need to make sure, we're comparing the same slice of an apple to the same size slice of an orange. Okay. So those are the things we need to do this. So in this particular internal work, we chose a study area where we have done quite a bit of work previously, and also where we have basically an existing or close to an existing sort of black box water balance model that's not tied to another project or anything like that, so we can use it as part of our internal work. Okay. That area is the Dolan Creek Watershed, which is in Val Verde County. Dolan Creek would be a tributary to the Devils River, and it would enter the Devils River just upstream of Dolan Falls. Okay. So the watershed is shown in orange on the screen now. And that's the study area. And so that's, essentially where our black box model is, and we're assuming that's already built, and it's not really the focus of this work. The focus is how we, take that same model and what happens relatively given changes in inputs. Okay. So the next thing we need to do is we need to figure out a way to create our time series of historical weather data and time series of data representing potential changes in weather patterns or forecast changes in weather patterns. Because we're dealing with forecast quantities, we can't just, use a data set because it's forecast, so it hasn't been measured yet, right? There's no data available. So the one thing we can do, and that's been used quite a bit in the past, is we can use what's called a stochastic weather generator. Stochastic weather generators, those of you who work in water resources planning and things like that may be very familiar with them. They've been in use since at least the 1980s. And the idea with a stochastic weather generator is that you're going to summarize all of your existing weather data using probability distributions. And then you create a simulated time series of weather patterns that has the statistical properties of your observed data set. Okay. And so you do that, as I said, with a probability distribution, which provides a compact form to summarize a big data set. And then you'd use stochastic simulation, where you choose a random number, and that gives you a value from your historical data each time. So that random number that's used in a stochastic weather generator provides, because you use the same random number for your climate data set as your actual historical data set, that provides the way to link the two models, put them on the same basis, okay? All right. So now, to look at sort of the historical weather side of our framework, to figuring out this, what the relative impacts might be. We're using the PRISM data set for weather data in this project, so you may be familiar with that, but it's parameter elevation regressions on independent slopes model. It's available for the continental US, and it's technically a data product in the sense that it's a model or interpolation of data, weather data parameters to a 4-kilometer grid but it's all based on the existing gauge network across the US. Okay. So if we look at annual average precipitation in our study area, that's what's shown right now. And you can see we have, PRISM is gridded data, as I said, so the grid points aren't shown on here, but there would be many, many grid points, basically one for every 2 square miles. And if we contour the annual rainfall depths from those grid points, this is the period 1989 to 2018, which is shown here. Then you get a weather map like this, or I'm sorry, isohyets like this. And the one thing to notice is there is a definite trend moving east to west, so there is a spatial trend in the data. PRISM is is gridded data, so it's already gone a form of regionalization, which is rainfall data are traditionally collected on points, and so you need to regionalize it or make it apply to a larger area. So this has already gone, PRISM has already undergone a form of regionalization, but given these spatial trends, we need additional regionalization. So the first step in sort of processing our data to get, to look at sort of generating our synthetic weather time series would be to identify regions of similar data points. And so this is what's shown here. And basically the other sort of variation that we always have for precipitation data that we need to take into account, besides spatial, which would be regionalization, is seasonal. And so we have a different approach for each season. And so the discretization that's shown here is just showing we broke it into 4 regions. And these regions are areas where the rainfall data are statistically similar, like they have the same sort of mean, median, variance, skewness, kurtosis for the stations that are in each group. And a group is identified by color. And so that's done for, all 12 months to take care of any seasonality that may be in the data. Okay. Then we further need to keep describing our data set to make our weather generator. Another thing that's really important for this type of generating these type of weather time series are spells of contiguous days. So you want to make sure that you can represent having, long periods of dry days and long periods of wet, or not as long period of wet days usually, but long periods of dry days. And so the way to do that is to develop a probability distribution by month for, the duration of days that you might have that are dry. And so you do that using a histogram. Histogram is just, the count of the number of times you've observed, 1 dry day, or 2 dry days, 4 dry days. And so the green bars are the histogram, and then you fit a probability distribution to that, and that probability distribution is shown with the red line. The probability distribution in this case is a negative binomial distribution. That part's not really important, but what it does do is it provides a known equation to provide that line, and there's only 2 parameters that you need to calculate that distribution. So each of these months represent 30,000 measurements in the histogram, and so what we've done is we've gone from 30,000 data points to 2 parameters for each month. Okay? So it does provide a very shorthand, compact way of representing your data. The other thing that it will do data-wise, if you have a large number of points and you're doing a probability distribution in histograms, you don't have to worry about outliers as much, assuming you're saying I have a very limited number of outliers as well as a limited number of bad data points. They won't show up, or they'll basically be ignored for the most part in the distribution fitting. Okay, and then this is just showing the other 6 months for dry days. The other sort of parameter that becomes pretty important in the weather generator would be the amount of precipitation on a day. And so this is the same sort of treatment. Again, we take all the data, make a histogram, and from that we're developing, fitting a line to it basically. That happens to be a probability distribution. It gives us a compact summary of all our data. And so those are kind of the things we need to simulate our daily time series. Okay, so we have our daily time series for the weather data, And we can run that through our water balance model that provides sort of one side of our calculation. The other side of the calculation would be the part that has the changes or the trends in long-term average weather patterns. And so we'll get that from global climate model output, and that comes down the other side, and the idea is then we're getting our two values, we compare those, we're getting a simple representation of relative recharge and what sort of the impacts or risks will be given the possibility of hypothesized changes in weather patterns. Okay. So to get we've seen the weather data portion of this portion of generating recharge from historical recharge, we'll say. Now for the global climate model portion, what we have to do is what we can do is we can rely on climate models, basically global climate models. There's a thing called the Coupled Model Intercomparison Project, and it's basically just a consortium of various research entities that have gotten together and decided, what a series of models should be to test all the possible scenarios from sort of the ocean atmosphere perspective across the world that could lead to different sort of climate trends. Okay, so the current phase of this project is phase 6, and so that's ongoing. All the simulations are still being done and still being formulated. The most recently completed phase is phase 5, and so for that, all the model output are available. Anybody can download them, access them, and you've probably all seen lots of sort of comparison results from these models at this point. But the two goals for phase 5 were to evaluate how realistically the models are in terms of simulating known values, as well as to provide projections of future average weather conditions out to basically 2100. Okay, so basically it provides a synthetic data set to use to estimate what could be the different weather patterns given changes in climate, changes in long-term average weather. Okay? Within this phase 5 data set, there are 4 core simulations, and those are, the definition for those are shown on the screen. It's probably not really important, but it's just provide a spread of values, basically. The 4.5 one is the one that's considered sort of the median scenario, maybe the most likely scenario, and then there's low case and high case scenarios. Okay? The one other problem we have with trying to use climate forecasts, or actually the global climate model output for this type of study, is that it's global, so it's by far too coarse to apply to like an individual watershed. So there's a whole bunch of downscaling procedures that have been developed by various people, various climate scientists. Unfortunately, it's all, most of it is available already downscaled. And so there's a link on the screen where you can access the downscaled projections. So really what it's doing is, that's already available. It's provided through a consortium of research institutes. And there's 2 sort of common downscaling methods that are used for this. And those are the localized constructed analog and bias correction with constructed analogs. So in the end, what all this really provides is we have 4 scenarios, and there's 30 models that are in this project, 30 different models, and we have 2 downscaling methods. So what that gives us is 30 times 4, 120 times 2, 240, basically 240 model output time series. Okay, and that represents the climate change. And so each one of those is just treated like a historical data record, and we can give it the same sort of process, and that's how we get the climate change portion. Okay. So just to refresh on this, everything is expected to vary spatially as it's weather data or weather projections. And so this figure shows the various grids and identification points that are involved. And so the prism which we saw for the data are in blue. That would be the blue grid cells, as well as The blue points would be the centers, and then there's a black dashed grid. That's what the various downscaling methods use. One uses a 1/8 degree breakout, and so those would be the gray squares in the center of the black grid, and the other uses a 1/16 end, and so those are the more higher resolution dark gray squares. Okay, so at the end of the day, basically it's a lot of results, a lot of data. A lot of data and a lot of soft information, where the climate change projections would be soft information. All right. So, as I said, this is kind of a work in progress, and we're kind of going over what the various methods are. And so the next steps are basically to break out the climate values or the climate projections into climate periods, 30-year duration, and then to go through all of the statistical processing so that we can make an appropriate way to get those time series for comparison. Okay? And so the real goal with that part of it is to just generate these weather generators, let us provide, values for each synthetic simulated day that are on the same basis, what would be the forecast change versus the historical value. And at the end, the real goal for all that framework is to take really all this data and information, which is really, tens of gigs of data, as well as soft information and climate projections, and provide a sort of simple comparison graph that provides something actionable. And so what that is it's, the relative change in recharge going forward in time. And that change is, what would be projected from the climate simulations versus historical data. And so, as I said, there's no actual results, so this is a hypothetical graph, but this is what we're going for, something that shows, the probability of this change in recharge, which then gives something actionable in terms of planning and design scenarios. All right, and that's all I have. Questions? Thank you.